Hi everyone, it is very nice to work with you in the summer school of the Essence project. This lesson is a part of the subject Power System Analysis, and the lesson today focuses on calculation and analysis in photovoltaic PV integrated systems, which could be a standalone one or a system in the connection with a grid. First, let's enter section 1 to talk about photovoltaic cells. A PV cell is comprised of many layers of materials, each with a specific purpose. The most important layer of a PV cell is the specially treated semiconductor layer, in which it consists of two distinct layers, N-type and P-type. At the N-type layer, there are gaps so that photons from sunlight can penetrate into the PN junction, PN junction, and strike the free electron to produce an electron flow, which flows from N-type layer through the load to the P-type layer. And thus, there exists an electrical current from the P-type layer, which is the positive pole, and through the N-type layer, which is the negative pole. And on the surface of the cells, you may find that the gaps appear as tiny white color stripes on the PV cell surface. The produced electric current is called IPV and is expressed as we could see here. And also, we can find the related parameters defined like this. Accordingly, we may develop the PV equivalent current source diagram as shown in the diagrams below. On the left hand side, this is the ideal equivalent diagram, while on the right hand side, we call this the practical diagram of the PV. In the practical diagram, we consider the existence of the line resistances in series and parallel connection, which represent the power dissipation in the PV cells. The current going through the diode ID is specified by the below stated parameters, and this part is the ID current in the ideal diagram, while this part is the ID current in the practical diagram. As you may find over here, RS resistance is taken into account. From the ideal equivalent diagram, we may see that the output current I of PV cell is the difference between the IPV and the ID currents. To visualize the current variation, we usually use the volt-ampere response as shown in the bottom right of the slide. IPV is a constant at a specific solar radiation. That's the reason why it appears like the horizontal straight line like this. Meanwhile, the ID current appears as the red color curve. Therefore, the output current I of the PV is IPV subtracted by ID. Okay. When we do the short circuiting, the two output ends of the PV The output voltage at this moment is of course 0, and the current I becomes I short circuit, ISC. And you will find that that working point is right here. This is the first special point on the VA response of PV. However, it should be noted that this is only happening in the ideal circuit, while in the practical circuit, the real value of ISC is a bit lower than the IPV because of the existing losses. Now, when the PV is kept open circuited, the current I equals 0 at the open circuit voltage VOC. Okay, and we have the second special working point right here. Finally, one could find the shape of the photovoltaic IV response as the green color curve over here. When solar incidence varies to different values, for instance, 1000 watt per meter square, 500 watts per meter square, or 200 watts per meter square, we may obtain different IV curves like this, right? 1000, 500, and 200. Even at the same solar radiation, okay, for example, we have the same value of irradiance 1000 watt per meter square. When the PVs are working at the different working temperatures, you will find that we also have different curves, IV curves, okay? For example, the green one is with the working temperature of 75 degrees Celsius. The blue one is with the working temperature of 50 degrees Celsius. And the red one is with the working temperature of 25 degrees Celsius. Of course, we can see the lower the working temperature, the better the performance of the PV cells. This reveals that the PV output efficiency depends on its working temperature, and it is approximated by scientists that the efficiency reduction rate is about 0.4 to 0.45% per degree. Calculating the output power P equals U times I, and then sketch P on the diagram, we may find the PU, or power voltage plots of the PV. So, for example, over here we have the IV plot in red, in blue, or in green color. We also infer the PV curve in red, blue, and green color respectively. Similarly, for the curves in different temperatures, we may find the same thing. It is an important note that on each of the PV curve, there exists one maximum point, okay? Each of this, we have a maximum point. This is the maximum power point that the PV cell can achieve or can work at in a specific condition of environment. And the maximum point is related to the best working point on the related IV curve, no matter what the solar incidence or working temperature is. So, The equivalent electrical diagram of a PV is a current source diagram with the participation of a diode, as you may find over here. When output short circuit happens, the short circuit current ISC does not exceed a specific maximum value. Usually, in the commercial PV, that value is about 7.49 amperes. Therefore, we may note that this equivalent current source does not have a wide range of short circuit current values and could not reach to the high short circuit currents as found in other electrical generators. We can also create an equivalent voltage short circuit for PV as the following. By using Thevenin-Norton theorem, we can create the structure of equivalent resistance in series like this. The parallel resistor in the current source circuit is replaced by RSH over here. As above mentioned, the solar incidence in general continuously varies in an uncontrollable manner. It is because of the natural condition. In order to obtain the most electrical power from the PV system, the load that sits over here must be and could only be adjusted relevantly to be equal to the internal resistance of the PV system. This could be done by inserting a maximum power point tracking MPPT module into the PV circuit system. The principle here is that we combine this DC-DC or DC-AC converter together with the load as a new equivalent load Z prime. And by applying suitable control algorithm, we could keep Z prime equal to Z in during operation. One more important fact, which is worth our careful note, is that for big PV systems covering a large area, partial shading phenomenon usually happens due to various reasons, such as clouds, trees, flying objects, etc. This may cause uncertain deformation of IV or PV curves of the PV system from the gray color shape into the blue color shape. So, like this, over here, and over here. Therefore, there appear many local maximum power points, but none of them is the unique global maximum point of the system anymore. You will find over here some local maximum points, okay? Accordingly, the MPPT module faces difficulties to identify the best working condition for the whole system, which has already had uncertain incident power. To limit this highly accumulative uncertainty, it is suggested to restrict the serial connection between the PV panels, but do the parallel connection instead. This could be explained as the following. When we connect them in parallel structure, if any panels experience shading phenomenon while others don't, all panels can still work with similar output voltage values, although the current or power flow contributed from each of them can be different. Right. Thus, with the support of the maximum power point tracking system, we could keep all the panels working at their best output power condition at this point, okay, at these points. Meanwhile, if the PV panels are connected in series, they will share the same current value. This leads to the fact that the output power produced at each panel is not at its best efficiency, and the common current is significantly reduced. In a typical PV power system in resident houses, we may find that the load curve in terms of daily hours, as shown in the blue color diagram over here. The peak consumption hours usually fall in the second half of morning till noon and the late afternoon till evening, right here, okay? Meanwhile, the power supplied from the sun concentrates the most at noontime till the first afternoon half, as shown in the red color diagrams. In addition, it depends tightly on the variation of solar irradiation. Unfortunately, there exists the misalignment between the consumption peaks, okay, and the supply peak. We cannot shift the supply peak, which follows the natural rule. Therefore, it could be concluded that the standalone PV electrical source is uncontrollable. Meanwhile, to keep the supply voltage at a constant value and to keep the whole electrical system of the house stable, the consumed power or the demand power must be kept balanced with the supplied power or the amount of power which is produced by the PV system. Therefore, in the resident PV system, it is usually connected to a battery energy storage system and or a providing generator. As you may find over here, the ideal system will include both battery and generator, the local generator. Also, the whole system is connected to the grid line at the house location. In this way, the house is fully equipped with all possible electrical power sources: the grid line, the generator, the local generator, and the energy storage system.